So we have talked about what machine learning is, and from next week, next chapter, we're going to talk about some specific machine learning algorithms. And before doing that, I want to introduce sklearn, which is a simple and quite efficient tools or a package for data analysis or machine learning algorithms. Okay, so sklearn includes a lot of well-established machine learning algorithms in Python, and it is open source and it's commercially usable with the BSD license. Okay, and then it is built on the NumPy and SciPy and Matplotlib, and more importantly, it is well documented with many examples, and you can download this. You can check this as sklearn here. So in this homepage, you can see this classification, regression, clustering, and dimension reduction, model selection, pre-processing. So pretty much all the popular machine learning algorithms are already implemented, and you can just simply install and you can just import and you can just enjoy. And there are four key classes. So these are implemented as classes. So you can check these classes here. So data set and models and evaluation metrics and experiment. So data set includes some kind of toy data sets, popular data sets. And then models include pretty much all the machine learning algorithms here. And the evaluation metrics includes how to evaluate, how to calculate accuracy and some evaluation metrics. And in experiment class, there are a couple of methods for experiments. So when we split the data set and when we cross-validate, so these functions are available in this class. First, data set. Okay, and as I said, sklearn comes with a few small standard data sets. And these data sets are already in there, so you don't have to download. Okay, so these small data sets are already in this sklearn. So if you when you import this data set, then these data sets are already there. Okay, so Boston data, iris, and diabetes, and this. So these data are actually the popular standard UCI dataset. The dataset in UCI repository dataset. So these are toy dataset. So from sklearn datasets, you can import load iris, and then you simply call this function. Then now we have x and y. So we have 150 data samples, and x has 4 features, and y is just a scalar, 150 scalars. So we have 3 classes. Okay, and so when you print out x, then it looks like this, just the 5 samples. So each sample has 4 features, and the y is a value of the classes. So 0, 1, 2. Okay. When you load the data set, then you have to be careful about the dimensions. Okay, so many times this is the dimension n samples and the features, and for y we have just n samples, but you have to check. Okay, all the time you have to check, because sometimes they have different kind of dimensions. Okay, it could be features, it could be samples. Okay, so every time, whenever you check, whenever you download a data set for the first time, then you have to check. And in models, there are pretty much all the machine learning models. So from sklearn tree, you can import the descent tree classifier, descent tree regressor, And from sklearn neighbors, you can import the k-neighbor classifier and k-neighbor regressor. And from ensemble and SVM linear models, you can import many machine learning algorithms. And once you import, let's say k-neighbors classifier, and then you can make an instance of this classifier like this. Okay, so if you don't know what KNN, but it's okay. But KNN is one machine learning algorithm. Okay, so k-neighbors classifier is actually KNN, and then we have to pass some parameters. The number of neighbors should be 5 here. Okay, and then now we have a model. Okay, so this model is just one initialized model, and then we have to train, and once the model is trained, then we can predict some things. Okay, so when we print this model, then you can see this definition of declaration of this classifier. So there are many kind of arguments. Okay, so as I said, there are many machine learning models, supervised learning and unsupervised learning algorithms. And as I said, models are well documented here. So if you go there, for example, k-neighbors classifier, then you can see all the information about this function. Okay, so we have many arguments, and then all these arguments parameters are explained here. So you can check what this specific parameter means, and then you can actually, when you make an instance of this classifier, then you can pass some proper arguments to these parameters. Okay, so each model has this kind of structure. Okay, so there is a init constructor, and then there is a fit and predict. Fit is a function to train the model, and then predict will actually predict the class or the value if it is a regression problem given this input x. Okay, so when we predict, we actually use the model. Okay, so you have to call this fit function first, and then you can call this predict. Then the trained model will predict the output y given this x. Okay, so this is one example with the k-neighbors classifier. So this is this line means we created the model, or we just make one instance of this classifier, and then we train. So since this is supervised, so we have x and y. Okay, and then we train the model, and then we can just call this predict to predict the output given this input x. So the output looks like this. Okay, so this is it. Okay, it's quite simple. So first you have to import this classifier from sklearn, and then make an instance and call fit function, and then call predict. That's it. And this is not just about the k-neighbors classifier. So if you import any classifier, any other regressor, basically it's the same thing. So, okay, make an instance and train the model with the fit function, and then call predict. And the evaluation metric. So as I said, there are many kind of evaluation metrics like accuracy and the precision, and recall, F1, and some loss function. Okay, and also there are mean squared error and mean absolute error and R2 score. So given these two vectors or two lists, so this one is the output of the model, and then this one is the labels, true labels. And then given these two lists, then we can actually calculate the accuracy of this prediction. or we can calculate the mean squared error between these two. Okay. And if you want, you can just simply implement all these functions by yourself. But when you implement, you increase the probability to have a bug. So if possible, just to use these functions to be safe. Okay. Okay, and the last one is experiments. And when we do some experiments, then we have to do many things, like we have to split the data, okay, and then we have to cross-validate, something like this. So given the data set, and then we want to split the data like this, so we can call this train test split function. So we have an input x and output y, and then test size is just 20%, and then this function will split x and y. Okay, so when you split, when you implement these kind of things by yourself, then you have to be careful because we have x and the y. Okay, then when you shuffle this data, usually when we split, then we randomly select like 80% and or 20% from this x and y. So random select means usually we shuffle and then we select first 80% and the last 20%, something like that. Okay, in that case, when we shuffle, this one and this one, they are a pair. So if we shuffle this one and this one separately, this one is x and this one is y. If we shuffle these two, x and y, separately, then the data set is just messed up. Okay, so when we shuffle, we have to connect these pairs and then shuffle and then we split. So this function does that. Okay, so if you want to implement everything from scratch, then you have to make a connection between these two, and then you can shuffle and then select. Otherwise, just use this function. Okay, and then cross-validate. I explained cross-validations before. So given this classifier, this is another classifier. So CLF is one classifier model, decision tree, and then we call this cross-valid function passing this model and x data and the y data, and then we are going to use this accuracy to evaluate, and then we use tenfold cross-validation. Okay, so based on this tenfold cross-validation, we check how good this function, this classifier is. Okay, so this is the final example. We're gonna use random forest here. Okay, so this one is actually from import. Okay, and then first of all we split the data, so now we have training x and training y, and test x and test y. And then we make an instance of this classifier, and then we have parameters. These are hyperparameters. So since we have three numbers for this number of estimators, we have two criterions. So we have 3 by 2 means we have in total we have 6 configuration of hyperparameters. Okay, and then we want to know which configuration is the best. So we have grid search cross validation. We call this function passing this model with this parameter set, and then we're going to use accuracy, and then with the 5 cross validation, 5-fold cross validation. Okay, and then we train, and then we got the results here. Grid search dot best prompts. Best prompts. This one is actually hyperparameters. Okay, and then best CLF is grid search best estimator. So best estimator is the the parameters, the trained parameters with the best configuration here. Okay, so this is our best classifier. And then now we have a trained model, then we can just simply call predict, and then we'll pass the new data samples, test data samples. This is prediction, the output of this prediction. And then we can calculate the accuracy by calling this function, passing the target and the prediction. Okay. And then in this case, the best model is trained based on this 5-fold cross-validation. So now we can have a final training. So we want to use all the samples, not just 80%. Okay, we want to use 100% of the data samples to train the model. So there will be test samples somewhere. Okay, but we don't have that test samples. So we have X and Y. So we're going to use this X and Y to train the model. So from here, we know which hyperparameters are the best. So we're going to use these hyperparameters, and then we will train this model with X and Y. So now this final model is the best model. Okay, so here, this best CLF is the best model when we train the model with just 80% of the data samples, and then we evaluate all the configurations with the other 20% of the data samples, and then best CLF was the best. But we want to use all the training samples, X and Y. So now we got the best hyperparameters, and then we make an instance of the model, and we train this model with all the samples. So now we have a final model. Okay, this is it.